Right. The topic on data transformation is very useful topic. In various cases, we already noticed that not all the attributes are very important in modeling. And some models, they have feature selection inherently within the algorithm. For example, if you look at decision trees, you have noticed in our TOEI problem with the data set, we started with 4 attributes, but in the implementation, you have noticed just 3 attributes, which indicates that not all the attributes are important, or not all the attributes are get selected when we are modeling, right? And at the same time, some applications where you have very large number of attributes, you have a huge number of attributes. Normally, we call high dimensional data, and this is the area that actually I did my work in my postgraduate studies as well, where we need to identify a compact representation. What I mean by compact representation, when you have your data dimension gets really high, your algorithm performance will be very poor. So one way to reduce the size of the data and size of the attributes you have is you either select attribute selection, you select set of or subset of attributes from the original, or you can transform, like for example, principal component analysis. So that's exactly what I'm going to discuss. Right. Now, if anybody asks me why you need to make a feature selection, we can talk about multiple things. One of the things is, for example, when you want to improve the accuracy of the model, that means, let's say in this particular graph, we are actually trying to reduce the error. So when you are reducing the error, you will see the model complexity, right, is a problem. So therefore, we need to identify a balance between, your training error. So ideally, what you might notice is when your model get really complex, you will get a very good accuracy in training, but you will see after some point your error in test will increases. So if you're getting a better accuracy in training, but if you're getting poor accuracy on test, we usually say that this is overfitting. The term overfitting refers that your model tries to represent your training data as it is. Thereby, when you get new, you will get poor performance. So related note, there is another term called underfitting. So sometimes when you're building models, you might notice that you will get poor accuracy in both training and testing. So in that particular case, we say that your model actually underfits. Okay. So the what I want to really answer the question is, why do you need to make feature selection? So when you are selecting features, you can avoid the issue of overfitting. Second, by reducing the number of features, that means your model gets simpler, which means you can interpret your decisions. Like for example, when you have like small number of attributes, it's easier for you to identify how you came to that particular conclusion. And at the same time, computation complexity, like if you take algorithm like nearest neighbor or distance calculations happens where like you have to consider about the distance from one point to the other point. So that also get reduced by reducing the number of features. So there are many reasons that actually you can see why you need to use feature selection. Right. Now, as I told you earlier in the beginning, we can focus on two things. We can talk about attribute selection or feature selection. That means you are selecting basically a subset of attributes. Right. So during when people work with the decision trees, they have noticed that when you add some random attributes, what do you mean by random? You can just create some random values and you can keep on adding. And experimentally, they have shown that the decision tree performance drastically reduce when you keep on adding irrelevant features. So on the other hand, what it means, when your data set has irrelevant features, ideally you will get a poor performance. Similarly, if you take like nearest neighbor like algorithms, what you notice is its also accuracy will be very, very poor when you have irrelevant attributes, right? That means if your attributes are not relevant to the concept that you are looking at, then the accuracy will be very, very low. Okay, so for example, in nearest neighbor like algorithm, people have worked on this particular area, and what they have noticed is depending on number of irrelevant attributes. So they have controlled the number of irrelevant attributes, and then they have observed how many data points you have to get a particular accuracy level. So they have noticed that the number of training instances, number of data points that you need to increase, right, with the number of irrelevant attributes. So you will notice that so many algorithms actually face the issue, but not all. For example, if you take a naive-Bayes like algorithm, it doesn't care. Remember, in naive-Bayes, we mentioned that it takes care of everything, and we assume that they are equally contributing. So it doesn't matter whether it's relevant or not. Naive-Bayes will not base on that, and so that effect is very minimal for naive-Bayes. But on the other hand, the relevant attributes can also be harmful. So therefore, so that you have to carefully select, okay, what should be the representative sample. Okay, now that we have got about some idea about the attribute selection and how different algorithms actually react on the number of irrelevant attributes. So let's see what are the techniques we have to select attributes. Now, first one is there are actually two ways of feature selections. One is you can select features independent of a particular machine learning algorithm. And this is called filter approach. Filter approach means that you assess your attributes based on some general characteristics, right? For example, we can use a measure like information gain and gain ratio or Gini, the measurements that we have discussed in decision trees. And that will be independent of a particular algorithm. So you can use some measurement and you can rank the features, and using the ranking, you can select, okay, what are the attributes that you are going to select for a machine learning model, right? So this is what we call a filter approach. Second one is you can use one method. You find smaller subset attributes that separate the data, and then you can use that one for that. Or else the second method is you can use a different learning algorithm. Okay, so let me give an example for this. Remember the 1R algorithm? So although it's a classifier, it's just very simple. I told you, like, it's not really used in practice, but you can use it as a feature selection method. You can run 1R, and then you can identify, okay, what is the best feature, and then you can keep on repeating to see like what are the other attributes get selected as the best one, and then you can use those attributes for a decision tree, right? That's one way to do. And another note is you can use decision tree, and decision tree serves as a feature selection method because tree selects features, and those features can be used for other classifiers such as support vector machine. So those are like some of the ways actually people actually use this, right? So those are the ideas, but ideally what the general practice for this is, usually we use some characteristics to evaluate all the uh, features, and then you select the best subset, right? So ideally you can use a ranker, right? You can use ranker. So you can rank sorted based on the measurements, and then you select the best ones. Right. Now, selecting subset will not be an easy, right? Why I'm saying that is, if you look at feature subset, right? Feature subset is very, very difficult task. So searching attributes for the feature subset, you will notice that if you look at our simple data set on weather data, you can see how many subsets are possible. So this is called feature space for weather data set. Why I'm saying that this is as a feature space for weather data set, you will see that from the top, you start with empty attributes, where you select one attribute at a time. So when you say a weather data set, I hope you remember we had attribute outlook, temperature, humidity, and windy. So in the first level, you select only one attribute. So these are one attribute subsets. So you can see in our case, we have four. Then you can take two attribute subset, which means that you with outlook, you can take temperature, outlook humidity, outlook windy. Then we can take temperature humidity, temperature windy, and finally humidity windy. So you will get six, right? Two attribute subsets. Similarly, if you look for three attribute subset, then you can get four. And finally, when you select everything, and this is what we have, right? So how many subsets then? So you have four features, right? So you will notice that how many feature subsets we got, right? So this will be huge. So for example, I have a question for you. If I have five attributes, what is the how many feature subsets are possible if you have five attributes? Yes. Right now, we have four attributes. I will repeat the question. And if you go through the how many subset we can create, we start with the empty subset. Then you will take one attribute time, you will get four. Then you will get two attributes, then you have six, another four, right? Then we have another one, like how many then? You will get about 16, right? So if you have a five, what do you think? Yes, any answers? Okay, I'm getting some answers. Yes, is it 32? I'm getting majority. Yeah. Check here, let me know, but I think you can go with 32, but explore and see, right? So you can think if you have just, one attribute, then you have two, right? If you have one attribute, you have two possible, empty and just one, right? If you have two attributes, right? How many? So if you have two attributes that you have empty set, then you can take one attribute at a time. Then you have take both. So you have four, right? Ideally, if you go on this fashion, we are getting 32 feature subset. So which means, right, if you have 100, you can imagine, right, it will be 2 to the power 10 then. So when you have increased numbers, you have exponential growth in number of feature subset. So if you are trying to evaluate all possible combination, now you will notice that it's not practically possible, right? Practically, it is not possible to evaluate each of these subsets. It's possible for a small data set. Now think about, in some data we have like about 10,000, 20,000. Think about text data, for example. You have billions of features, which is impractical, right? So you will see. So it's not an easy task, right? So how do you search? In this search space. So that means this is our feature subset, right? Now we have to search which one is best. So what are the searching techniques that you can think of if you're using? Right. Now, one thing that we have realized is number of attributes subset is exponential. It's number of attributes. So in our case, if you have n attributes, we have realized that it should be 2 to the power n, right? So which is a problematic one, isn't it? Yes. Okay. Right. The next one is there are many techniques you can actually think about. You can search for this, and uh, in practical implementations, you will see there are many techniques are there. But let me at least explain the common ones. Right. Um, so what we want to discuss is the first is you will notice that the common ones, greedy means you are looking for all possible combination. The first one is you can go for forward selection. Now, forward selection means you start from empty, then you add one attribute at a time, then you select the best one, then you add a two at a time, you select the best one, and so on. You are going in a forward direction, keep on adding the features, right? That is called forward selection. Second technique is you start with all the attributes, you eliminate one at a time. This is called bottom-up strategy. In bottom-up strategy, what you can do is you can start from, in our toy problem, we can start with 4 attributes and you remove one at a time. One at a time. So in this way, you're exploring all the possible combinations, but removing them. And this is called backward elimination. Right. Next, there are many other. So you can notice that you can, most of the time, these things can be done in parallel. So bidirectional means that actually you can use both the techniques together. You can go from bottom to top and top to bottom. And then whenever it meets, right, then you stop. So in bidirectional, what happens? In one side, you start with the empty set. The other side, you start with everything. So empty side, you keep on adding. When you start with everything, you keep on removing. And whenever it means you stop at that point. This is called bidirectional search. Best first is a search algorithm. We can use a graph and we can choose most promising node, right? You can use some specific rule for this one. And you can add feature with highest performance, right? So that's way we can go for best first search. Then we have beam search. Simply, we are using some heuristics. What we can do is you can expand most promising node in a limited set, we normally say. When I say a limited set, and you can use the best one, for example, right? So it's that's why it says it's an approximation to the best first search. Right. Genetic algorithms are, have you already learned about genetic algorithms, or is it the first time? Can anyone let me know whether you are familiar with the idea of genetic algorithms?
First time, sir.
Okay, so then let me explain this one. This is again actually coming from the artificial intelligence, and I hope it will be covered at some point. But let me explain in simple terms how this may used, right? So sorry, we talk about bidirectional, best first, and deep. Okay, let me explain a little bit about genetic algorithm because it's a very promising one, right? What really genetic algorithm means is ideally, you know that when we talk about parents and the child, some of the features, we realize that, okay, some of the features or some of the characteristics actually coming from parents. And this is the idea that they have used in genetic algorithm, the use of genetically transform these ideas into childs. So that means based on the starting point, the next set actually you use from the previous step. So that's the idea we will use. So ideally, what it does, you will have a starting set, and then you will use that starting set to generate the next one, right? So that's the idea in genetic algorithms. So if I give you more information on this, it's like this. So there should be a way that you can evaluate as well. So for example, now when you take the features, ideally what we expect is we want to create another representative set, right? So ideally what we can do is you can start with something and then you can use that for generation. So everything start with in genetic algorithms, what they say is they start with something called chromosomes, and you use that to generate new one. So ideally, we can represent the chromosome as just a set of numbers, and you can either represent them as in our case we can represent them in, for example, in binary. And the next interesting thing is operations that you are going to use. This is called evaluation. For example, we can take a person's information, and then you can use that for that one. So ideally, you have a chromosome representation, and then you have evaluation function. So you have evaluation function here, which will evaluate this, right? And using that evaluation, we can evaluate each of these generations, how good they are, how bad they are, then only select. So when it comes to attribute selection, what happens in the genetic algorithm, you can read about this. So you can generate a feature subset, and then you can evaluate the feature subsets. And by doing so, you can identify what are the best feature set. Now, for that, they talk about some operations as well. For example, let me explain the basic two. Maybe I will explain crossover and mutation. Now, crossover means that I told you, like, you start with the two subsets, for example, and then you can actually select a part of the first one and the part of the second one, and then you can combine. So ideally, what we can use is, you can start with some two feature subsets and combine part of the subsets to create a new subset. This is called crossover. In mutation, what you do is you make some changes in the feature subset. For example, you can remove uh, something existing and you will get a new subset. So that's called mutation. Ideally, mutation, what it does is actually you change the values. So for example, if it is a binary representation as 1 and 0, so what mutation means is you change 0 to 1 and 1 to 0. So it's a very interesting one. You can look at look at this genetic algorithms. Actually, it's quite useful. So also you can explore this in, for example, in your thesis, like whenever you want to explore which are the best one, right? The ideas that I am actually said was, like, you start from some feature subset, and then you can create new feature subset using some of these techniques. I explained crossover and mutation, where you actually combine, parts of two subsets to create a new subset. It's called crossover. Mutation, actually you make some changes to existing feature subset, where it will generate a new feature subset and you evaluate that. Now, when I say evaluation function, now since we talk about feature selection, what we could use is, um, we can use classification accuracy. For example, the measurement could be, in our case, you create a feature set, and then you evaluate using accuracy, for example. That's the way that we can use. Okay, maybe what I could do is, I can explain this in the implementation so that you can explore more, right? Okay. But remember that this should be done in a detailed fashion, how exactly this will work. And I hope it will be covered in your AI module. Right. Now, going forward, what we have discussed so far is feature selection using, how should I say? We explain the feature selection by selecting features or feature subsets, right? And what we have considered is use of some independent measurement, right? So we are not going to incorporate any machine learning algorithm. So all the techniques what we have discussed so far is independent of particular machine learning algorithm. Okay, second type we call wrapper method. Earlier we discussed filter method. In wrapper method, we actually use a particular machine learning algorithm. So we can use a particular machine learning algorithm, and we can perform, for example, cross validation, and then we can evaluate. Again, this is time consuming because it's greedy approach, which means that you can evaluate all possible feature subset. So our toy problem, we had 16 feature subset. We had 4 attributes. So you have to evaluate all the 16 in this fashion, and you select the best one. Okay, so one addition you can do is, maybe you can rank the attribute. So if you have done this, then you can reduce the time consumption, right? Okay, then how are you going to stop, right? So again, like I said, ideally you want to evaluate everything, and I know it's not practically possible. So what you can do is, you can see whether your feature addition is improves your accuracy significantly better. And remember, we discussed we can use some statistical tests for that. And you can use that to make that decision if you want to stop early. Otherwise, naturally, what you do is you evaluate all the possible feature subsets and then you select the best one. Right. So the next thing that I would like to discuss is feature selection. What we finish. Feature selection means you are selecting a subset of features. And we discuss two techniques, filter approach and wrap approach, right? The next one is about feature transformations, we say. What I mean by feature transformation is you create a new feature set. That's called projections, right? So simple transformations, what you do is you can make some changes. So we actually transform sometimes features as well in, for example, process in initial processing. Now, for example, if you have two dates, we can take the differences. So it's a simple transformation. You can take two ratios of numeric attributes, right? Or you can combine two attributes together, right? Or else sometimes you can cluster the data and then you can use that cluster information. So that is also some projection we can use. You can add noise, some randomness into data, and then you can remove data randomly or selectively. That is also another transformation, right? So those are the simple ideas that actually we can talk about in projections. But what really I want to discuss is some standard techniques. And when you explore standard techniques, there's a very interesting one, commonly used one is called principal component analysis. So in simple terms, I'm not going to go into mathematical basis that one. So ideally, if you want to understand the mathematics, what you want to do is you start with the data metrics. You have to create covariance metrics and so on. So there's a mathematical side of this to understand this. But at this point, what I want to emphasize is how it works and how we can actually make use of this in our machine learning problems. Right. Now, ideally, what principal component analysis does is it actually transforms your actual data into um, as a new set of features. You can say that it's a transform space. So in this particular example, you will see you have three-dimensional graph, and then you will see some data sets, and then with some class label. If you carefully look at this, you will see there are four classes. So principal components actually look data variances. That's why I said we have to create a covariance matrix. So it looks as the variances. So when you say variance means it's a spread, right? Variance means how vary the data from the middle point. So if you look at here, you can see in this direction, in this plane, you will see there's a plane here. This is the plane where you see the most variance in the data. So what principal component does is actually it identifies this the highest variance in the data. In this particular case, it will select this plane and then it will select the principal component, right? So our first principal components is along the highest variance. So you can see we can identify the first principal component in this direction. And after that, you repeat the process, but whenever you create the new principal components after the first one, should be perpendicular to the previous one. So ideally, you can select another principal component perpendicular to the first principal component. And this is for the second principal component. So after identifying this, and in this particular case, it shows you selection of first principal component and second principal component. And you can notice that the data is nicely separated, right? Okay, remember that you might not see this every time, but most of the time you see a better representation compared to the original representation if you use PC. So that's the idea. So ideally, this technique is very, very useful one way as a visualization tool. Any data set, you can find the first two principal components, and then you can use it to visualize. So let's say you have a data set, and then if you want to visualize, and we know that when you have high dimensional data, you can't visualize them properly. One way is you can randomly select two attributes and then you can plot it. And that's what we did in Iris. I hope we have done Iris. In Iris 1, we select the first one and the third one, and we see very nice representation. It will be very difficult if you have a large number of data points, right? It's not easy to select which two is the best one. So whenever you have a situation like this, okay, you can use principal component analysis. You select the first two principal components, and then you can actually plot. So ideally, that method guarantees that you select the variances. Wherever you see the highest variance, it clears the first principal component, and it's the common use. Right. Any question on this one? Right. So let's move on then. What happened is, as I told you earlier, you look at the most variance in the data set. You can see here the data is represented as the oval, and then you select the first principal component along with the highest variance, because this is the highest spread in the data you will see compared to the middle point. And then once you select the first principal component, the second one we select to perpendicular to the first one. Right. Although I am not going to give you the mathematical basis, let's discuss the algorithm. So what we are going to do is we are going to find out the important direction and based on the variances. So this can be used to get a different perspective of the data. So if you look at the basic representation of the algorithm, what you notice is you look for the greatest variance, and then it will select as the first principal component. And next is you are going to find out a direction perpendicular to the previous direction, and you repeat the process. So implementation, as I told you earlier, you start with covariance metrics, and then you find eigenvectors and eigenvalues. So you use a process called diagonalization. And again, there are many techniques are there how you actually identify the matrices, right? So if you're still interested in mathematical basis, I suggest you to read about this. Right. Now that we have looked at the principal components, the generation, I have another thing to discuss. Although I said the first two principal components, actually you can create any number of principal components. Ideally, if you have 10 data points, 10 features, then you can go for 10 principal components, right? But you will see not all the principal components are important. So if you look for a classification problem, then you have to select. If it is visualization, you can look for the first two. But let's say you are applying this for classification problem. So if you are applying this for classification problem, okay, then it's very important that you select, okay, how many components you are going to use. So ideally, what you could do if you want to identify this experimentally, what you could do is you can generate all the principal components and you select each and every one and to see how the variance happens, right? So in this particular case, what you notice is, I told you first principal component capture the largest variance. So here in this example, it shows you that it capture around like 61%. Second principal component capture 18%, third 4.7, fourth 4, fifth 3. You will see that when you go to other dimensions, other attributes, you will notice the variance diminishes. And then if you have drawn this as a graph, you see like elbow-like shape. Why I said elbow-like shape? If you carefully see after the third principal component, you see that very less variation. So that means we can think or we can use this as a measurement, right? We can select, for example, first three principal components. And if you carefully look at the first three, principal components capture the around like 84% of the variance in the data, right? Okay, so you can, to summarize what we have discussed on the principal component analysis, it's called a transformation technique, which converts your original data into completely new data set, right? New set of features. And this is based on the variance, right? Okay, so you can transfer data into space given by the components. So for example, I told you like you can use the first two principal components. And ideally, when you start, make sure that your data is standardized. What I mean by standardized is data should be in the same scale, either, for example, from 0 to 100, 0 to 1, okay, whatever the, range that you are going to find. So it should be the same. Otherwise, it might be biased towards the larger value, right? And people have actually used these techniques in very other places. And for example, people have tried to use these in decision trees. For example, there's a method called rotational trees. You can find this. Not a random forest, it's called rotational trees. In rotational trees, what they have done is like they have projected and use that projection to build the decision tree. Right. Any question on this one? So what we have covered so far, we completely covered the feature selection. And now we are discussing feature transformation, and we discuss our very first technique, PCA. In the lab class, I will discuss how to implement PCA, right? Any questions up to this point? Right. May I continue then? Right. The next one that I would like to discuss is another projection. Actually, this is my first paper, content of first paper. So I referred the book on Wake Up at that time, and the first edition of books. That's what I have used for my reference. And then my first paper is actually based on these two methods, PC and random projection, because I noticed that at that time when I read the literature, random projections were successfully used in many cases compared to other techniques. And I published my work on random, principal component analysis and the random projection on high dimensional data. And that paper actually got the attention for many other researchers. One reason is actually because I have noticed in the second edition of my book, second edition of the book, I noticed that they have included the new chapter on random projection. So I still have a very interesting evaluation when I presented this work in various different conferences at that time. And that is early 2026, 2006. Right. Going from this, PC is good. Actually, it's very interesting and it's quite extensively used. But the problem with the PC is it's very computational complex. The computational complex is very, very high. So why I am saying this? I told you calculating a PC is based on the covariance matrix. Now, what do you mean by covariance matrix? You have to actually like let's say you have 10 attributes, you have to have then 10 by 10 uh, metrics for this. So if you have 100 attributes, then you have to have 100 to 100. So if you have 1,000, then it should be 1,000 to 1,000, which is very, very, uh, um, how do you say, very complex to do that, and it's time consuming as well. So people were looking at the simpler techniques, simple projection instead of PCA, especially in a high dimensional space, right? So what people have proposed in random projection is simply you are using random matrix. So they call it actually random projection, but simply the idea is you are using a simple random matrix to transform. So what I mean by transform here, you have original matrix and you generate a random matrix and you simply multiply them. But when you're creating a random matrix, there are some ways that you should populate it. Although I said it's a random, it's not really random. So there are some ways that you should populate. There were like a couple of suggestions how you should do that. And if you do that, people have shown that random projection can preserve the original distances among the data in a very small factor. So ideally, this was very good and interesting observation I have noticed for nearest neighbor like algorithm. So I told you like I was working in these two techniques. So I was looking for a technique for nearest neighbor, and then I published this by combining this idea. So there's a theoretical basis for the random projection is also, that means although we are using a random matrix, that it will preserve the distances. So here are like my very early work on this. I'm just sharing for you to show you that what is possible and what might be like when you're working on this. So in these graphs, what you see is two example data set. The IRMA is actually medical data set, which consists of around like 60,000 data points, around 150, if I remember. I exactly didn't remember the number of classes, but it's definitely more than 100 data points. So 100 classes. So it's huge data set. And it's a set of radiography images. So that's about the X-ray images on various different parts of the body. The idea is how well we can accurately classify this, right? So the challenge for this problem was the high number of classes at that time, and it's very high dimensional as well. So when we observed this with the principal components, ideally with the number of components, it increases, and after some time, it actually decreases the accuracy. So there's a peak that we can actually observe. And when we use a random projection, it's simply randomly projecting it. And you can notice that it actually keep on increasing. Actually, we have tested about the 200 features. The original one consists of, I think it's more than 4,000. Because when I say 4,000, it's 20 to 20, right? So ideally, it is more than that. Second data set, what you have noticed is microarray data set. I have actually compared set of image data sets as well as set of microarray data set. The problem with the microarray is you have very high number of features, but you have very less number of data points. You have instances. So ideally, you have about like 100 data points, but then you have about like 2000 attributes. So again, we have noticed that when you apply principal component analysis, especially for microarray data, actually it fails. Fails means like you get a better accuracy, but then once you have more dimension, it decreases the accuracy. Whereas we noticed that PCA consistently improve in the actual accuracies, right? Without any of the methods, what you saw is original accuracy for the two techniques. So you have noticed that we are getting about less than, uh, maybe we are getting about 68% accuracy without any of these techniques. And here we are getting about 78% without any models. So this is just two, like if you're interested, you can read on this. I have given you the link for the paper. But what I want to highlight here is, you can use various different techniques to look for uh, improving the accuracies. And my observation for this is like we have noticed, especially when you have a very limited data points, we notice that random projection can outperform the PCA. And that was the conclusion of the paper. Right. I have actually related to this to you so that, I mean, like in future, since you are working on machine learning, and in this is also I know some of you are doing experiment just to show you like what are the things that you can actually do in this regard. Right. Now that we have discussed about the data feature selection and feature transformation, I'm going to look for some other techniques used in data transformation. Now, when we look at classification problems, ideally we look for like two class problems. But there's a problem sometimes. Some problems you cannot see them as, two class problems. Ideally in machine learning, you have to have data, right? If you have, when you want to make it as a classification problem. But for example, let's say if you have when you don't have data for all the classes, that how do you handle it? And that's exactly what I'm going to discuss in this part. Right. Now, some problems you have just single class when you're doing training, right? So the problem is we can classify, but it's very hard to find data, right? For some classes. So ideally, you can model as two class problem, but when you collect data, you have data only for one class. And that's the thing that I'm going to discuss here under the one class learning. So ideally, when you have a situation like this, then you cannot say it's a two class problem. You focus it as a one class classification problem. So that means either you will select the target, whatever the interested party, and then the other one we say it's unknown, right? So some problems, it's very hard. How do you formulate this one? So some problems you can reformulate. You can change how actually you represent it. But some you don't really have the class for the other data. Like password hardening means this is actually problem coming from the information security. That means like how do you say that your password is good enough, right? If you want to look for a machine learning, perspective for this is you can actually have data for better, but the problem is you can find negatives. What are the other passwords? So therefore, it's very difficult. Like, how do you say that? So ideally, you have some policies, right? If you remember, when you're creating a password, ideally they have some policies the length of the password. Like they say that you have to have at least 8 characters in the password. And sometimes they might also say that, okay, you have to have capital, simple, and so on. It is because that, some problem like this cannot be modeled in a machine learning way, right? For example, ideally, if we have like, good password and bad passwords, ideally we should be able to build a model which separate, good passwords from bad password. But what I'm saying here is it's really, really difficult to find out the label for the two classes. Right. Next one, another idea, it's a separate idea that I'm going to discuss. It's called outlier detection. So this one class, the classification that we have discussed earlier, we can use it as outlier detection, right? So why I'm actually say you can use the data and data spread. And if the data is beyond some point, then we can say it's outlier. So if you're using box plot in visualization, actually box plots does this. So what happens in the box plots? Ideally, you look at the mean value and the standard deviation. And ideally, if the data point is go beyond 3 times of the standard deviation that we have seen, we can call it as an outlier, right? So that's the way sometimes you can actually detect the outliers. Right. Another technique when we have to build a classifier, and if you don't have enough data for the second class, you can generate artificial data. I think with the recent advancement of AI, what is possible nowadays, I'm not going to say that this is the best way to do this, but people now capable of generate artificial data because the models are capable of identify the regularities, and based on the regularities then they can actually generate new data for us, and this is called artificially you can generate the data, right? So the problem that we have discussed early, where like you have data for one class and you have no data for the other class, then you can generate artificial data for the other class. So the advantage you are getting by doing this is once you can identify data points for both the class, then you can use any classifier that we have discussed so far. Right. So that's about the the data generation. Then you can generate uniformly random data. So ideally, I think we discussed from the very beginning the use of randomness everywhere. So when you have data for one class, the other class, the data we can generate randomly, right? Then there's always a problem, right? So if you've done it too much, right, then you might lose the information for the target class. So the idea of this previous one is if you're trying to minimize the classification error, so rather than doing it, so you can look for learning accurate probabilities. But then there's an issue. So this issue is called curse of dimensionality, which is again, I have used this repeatedly in my work as well. So the idea of curse of dimensionality means like when you have number of attribute, when it increases, and then it's difficult to separate the data, right? So ideally, you will get very poor performance. Right. So I think now we have finished our discussion on one class learning. To summarize what we have discussed, what one class learning problem is, how you may actually represent one class problems. Next transformation that I want to discuss, how do you transform multiple classes for binary ones? Okay, let me explain first one why this is important. Some classifiers actually, when they build or when they introduce, they support only binary classes. Binary classes mean if you have two classes only, right? For example, one typical example I used to give is support vector machine classifier. I think I have not discussed in detail the theoretical basis, so therefore I will spend a couple of minutes trying to explain what it does. So what support vector machine does, simply let's say you have let's say two class problem, right? Sorry, two attributes, then we can represent this as points. So let me say we have two attributes. I'm going to say this is x1 and this is x2. Ideally, if they are numeric, then we can have points. So let's say we have two classes. We have crosses here, right? And then we have circles somewhere here, right? So ideally, I'm going to give you this question. Like, if you want to separate them linearly, ideally, I could, right, draw a line to separate these two classes. So this is one way to separate it. The second one, okay, I can separate like this. Third one, I can separate like this. Right, let me say this is first one, this is second one, this is third one. I have a question for you guys, like which one you are going to select? Which one is the best? Is it one, is it two, is it three? Yes. Okay, I read your comments now. Gayan, you are asking one question. Can you explain me like what
Yes,
exactly you
sir.
want to know
Yes.
from me?
Yes, sir. Now, what I understood is that, sir, when selecting like a PC, you have to consider the correlation, is it, sir, between the attributes. And we are trying to reduce the similar correlated attributes into non-correlated attributes. Is it so, sir, in PC?
Okay, now if I go back this again, I'm sorry. If I go back to principal component analysis, is simply we use the term component to say that we are getting a new data points. It's a transformed ones. So when I say a principal component, which means you get a transformation of original data. So ideally, your transformation consists of all the attributes from your original data set. So simply you can think of, let's say, a simple transformation like you have linear weights. So you can see that so all the attributes in a original space is transformed to new space, and there we call components. The term components is, so you are getting a new feature or new feature based on the original features, right? That's what the component means. The secondly, when it comes to classification, we can, so since principal components capture the variances, the first one has the highest, second one has the second highest, and so on. You can select first few components if you want to keep the variances, highest variance in the data set. So how do you select? That's why I said you can look for the change of variances. When the change of variances is very minimal, we have seen an elbow-shaped curve. You can select the number of components based on that, right? And that can be used for classification. But if you read, you will. There are many people actually worked on PCA for decades, and some of the papers they have illustrated that okay, there's no guarantee that selecting the first few components will give the best accuracy. So people have shown that even sometimes you can combine multiple different components. For example, instead of taking the first three components, you might select the first component, third component, and let's say fifth component, right? That might be better than selecting the first few components. So it's actually, the machine learning is experimental science, and you have to select or you have to make decision based on what you observe and based on your experiment. So if you carefully plan, and if you carefully plan, and if you follow the correct procedures, ideally you should be able to identify, because all these is actually based on your data that you have selected. I told you it's domain dependent, and it depends on the attributes that you have selected and so, right? But ideally, Gayan, your question was like, what is a component? Components is a new feature that you have created from based on the original features.
Okay, thank you, sir.
Yeah. Going back to this one, so since I have not done the theory for the subvector machine, I just want to discuss. So let's say you have a situation like two features, and then let's say we have two classes like this. And what really we can use a linear separation, like I'm going to actually put a line to separate the two classes. But then I can draw it in various different ways, and my question was, which one is best? And only Dylan gave me the answer. And Dylan said one, like, what about the others? What do you think about the three cases? Okay, now I think you notice the problem, right? So all the three, I can draw more. So they can use to separate, right? Visually, we can see the separation. So this is the problem that people actually develop support vector machines. So what they have said is there are many, separations that you can identify, but support vector machines actually propose, right, maximum separation. So ideally, what do you mean by maximum separation? You are trying to identify there's a margin actually that's why we actually draw multiple lines. So we can identify margin here, right? So what I mean by margin, like, for example, anything, so if I go, like if I draw a line like this and parallelly a line like this, right? We can identify a margin of separation. And what support vector machine does is it tries to identify the largest margin. So where can I find the largest margin? Two parallel planes where this one. And then ideally, when you find the largest margin, you will see some of the data points lie in this line. So ideally, this didn't touch, but I want to touch this one. So whatever the attributes lie in these lines are called support vectors. So these are called support vectors, and that's how people came with the idea of support vector machine. So ideally, in what support vector machine does is actually it's try to find a separation. It's not just a line, but we call margin, which maximize it, and that's the outcome of the support vector machine. Okay, we were discussing something else. We were discussing transform multiple classes to binary one. Why I say that in original implementation of support vector machine, it supported only two class problem, and I think you can understand why they have developed for two class problem, because they were looking at separating data with highest margin. So with that said, originally when they developed, it support only two class cases. Right? Now there's an issue when you actually have two class problems. What's the issue is like when you have multiple classes, you can't apply. So early days, when you have more than two, like let's say you have three class problem, then you cannot apply, right? Support vector machine. So what they have proposed, how people have used then is you make two class problem from like more than two classes. It's like this. So for example, let's say you have three classes A, B, C. Ideally, what you can do is you take A as one class, B, C is as another class. In that way, you can actually convert your multi-class problem into binary one, right? So that's how they have actually, handled this issue. So then what happens, you will get multiple two-class problems. Why I say multiple? Because when you have A, B, C, this is three-class problem, but we are making it to two-class problem. Ideally, you are separating A from BC, then B from AC, and C from AB. So ideally, what happens, you convert this multi-class problem, multi-class problem into multiple two-class problems, right? Or else, there's another idea that they were talking about is you take as one versus rest, right? So you take one and then the remaining, right? One and the remaining ones. That's how you actually separate it, right? So this is how they have used this one. Ideally, if you have situation like this, you have to do for every pair of classes, and then you have to find out which one gives you the best accuracy. Right. I think it's almost 10 o'clock. Next part, I would like to talk about the ensemble, but I think I'll stop and talk about the implementation. Right. So I think I have ran this, right? So I have, maybe I can take this part so that I can start from the same page. So I'm going to use the same iris dataset. And we'll say X and Y, right? So 10-4 cross-validation comes from this. So I will put that here. We can say from scikit-learn dot model selection import cross-validation scope, right? And then you can have to calculate the scores. And this time, notice that we have to define the classifier as well. So let's look at the tree classifier. So I'm going to select the tree classifier here. I will share the code for you. Right. So I have selected the classifier as a decision tree. And then we calculate the scores using the 10-4 cross validation. Let me show you now, when you say score, right? So you can have, we can say print scores. You can notice here. So I'm sharing the code for you. Right. So you can notice that since this is run multiple times, right? You will get 10 accuracies, right? And you can see the variance. The lowest accuracy is 0.87, where the highest accuracy is 1, right? So that means when you are reporting, you can look for the mean. And so I will put it here. So we can say, okay, scores. Okay, so I'm actually putting mean and standard deviation because this is what is very important to report. So you can notice that in my run, I will get a mean accuracy about 96% with plus and minus the standard deviation and 0.04. So you will notice, and this is very, very important in the representation. Right. May I know how many of you have finished up to this point? Done? Finished? Maybe you can raise your hands so that I know you have finished. Okay. Yeah. Since I have run, it was not there. Yes, tree classifier should be there because we are using the decision tree. Ideally, I think I have it somewhere, right? Okay, we have tree. Yes. I will repeat, I will share the whole code again because we have to use the trees as well because I'm actually using from the previous code. I missed that part. So I will share the code again. So the complete code together with maybe the last part as well. So the right now, I think you can get the average accuracy. Okay, remember that when you're working for your final, so the thesis work, it's okay to use train test, but I'm not recommending it because we have already observed that the randomness plays a role here, and you can find out like 100% accuracy once in a while, and you can report it. No, it's not the way. To be fair with your experiments, you should report average accuracy, and ideally when you are reporting average accuracy, I highly recommend that you report the standard deviation as well, which gives you an idea like the uncertainty of your classifier. That means ideally how I might report, okay, my accuracy of this classifier is 96%, maybe plus or minus 0 point, plus or minus 4%, right? Yes. So in that way, you are giving, uncertainty of these classifiers. Okay, done, finish up to that point now. Okay, thanks. Now I told you tenfold cross validation is good, but ideally what we need is, you can repeat multiple times. So therefore, we normally recommend 10 into tenfold cross validation as well. So let me give you an idea about what this means, I'm going to give you a code for this. So what I'm actually going to do is I'm going to repeat 10-fold cross-validation 10 times. Ideally, the important part you are getting is now you have noticed there's a variance in your data. What do you mean by variance? Based on the randomness, once you split your data points, you will get different accuracies. And to get a better measurements, or if you want to reduce this variance in your result, it's recommended that you repeat 10-fold cross-validation multiple times. So I'm going to give you, in this particular case, repeating 10-fold cross-validation 10 times. The implementation is like this. We are creating a separate 10 by 10 matrix to store all the accuracies. And then for each fold, you are going to split into data fold, and then you are actually calculating the accuracies, right? So that's what you do. And when you run this, I will show you, you will get, 100 accuracies. So each run, you will have 10 accuracies. So you can see in my case, we have run 1, run 2, run 3, up to run 10, which will repeat 10-fold cross-validation 10 times, right? Ideally, this will reduce your variance, and this will give you a very clear idea of the average accuracy of your, classifier. So if you want to get accuracy of the each fold, right, then you should use this technique. When I say all scores mean, axis 1, average accuracies of the each run, because we have done 10 runs, right? Similarly, if you want to get a standard deviation, also you can report. Together with this one. So you can notice that the first run, you are getting 94 accuracy with 0.0, you have 94 with 6%, 96 with 4%, 94 with 6%. You will notice, right? Yes. And to get the final, that means if you want to average out everything, we can say, okay, print all scores dot mean, comma, all scores dot standard deviation. So now 10 into 10, right? So 10 into 10 for cross-validation. When you do that, you will now notice that the average accuracy is 95% with plus or minus 5% standard deviation you have noticed in this particular case, which is something that more realistic compared to if you just report just one 10-fold cross-validation. Right. That's all I think from my side today.